All right, so yesterday we did volume by disc, and today we're doing volume by washers. So you think of like a tool, if you know what a washer is. Sometimes people say volume by donuts, and you're going to see why in just a minute. So here we go. Find the volume of a solid form by revolving the area bounded by, so they all start off the same, bounded by y equals 0, so that's the x-axis. 4 minus x squared over 2, x equals 2, and x equals negative 2. So let me get my picture on that. And again, you could use your calculator to get these if it's a calculator portion. I kind of know what these guys look like. So 4 minus x squared over 2 kind of looks like this-ish. I have the y equals 0. That's not my, is here. And then I have x equals 2. So if you used your calculator, you'd see that x equals 2. This is going to cut it here and here. So my bounded region, again, just to not be confused, is actually this kind of weirdly shaped thing here. This is negative 2 and 2. Again, you can erase all that's left outside of that bounded region, and you'd be good to go. So the next question is, okay, so you're revolving that around the x-axis. So you get something like this. Well, as we learned from yesterday, this is a disk problem, isn't it? Because notice that the bounded region shares a side with the axis of rotation. So my R is always perpendicular to the axis of rotation. And so this is going to be a disk problem. So from yesterday, the volume is going to be pi. My bounds are from negative 2 to 2. Now what is my R? My R is this curve right here. So I really don't even have to, you've probably become a little faster at it. It's going to be that curve minus 0 squared, and that's going to be my volume. And so if I have this, I could get on the calculator, and I'm not going to do that part. I think you can type that in. I want you to stop the video and try, but you should get 144.094. Now let's look at this same type of question. Okay, find the volume of the solid formed by revolving the area bounded by y equals 2 and 4 minus x squared. Let's look at that issue. Okay. Okay, so we have our 4 minus x squared. We have that same graph. It looks like this. Now it says the area bounded by y equals 2. So again, I'm going to just cut that off because I like to just draw my bounded region. It's less confusing for me. Y equals 2 is here. And so here is my bounded region in there. And it says find the volume of the solid by revolving that bounded region around the x-axis. So do you see the difference in this problem and all the problems that you have done? Is that you have a hole. You have a donut. I mean, if you think about making this and visualizing that revolving, you would have a donut. So there's a hole in the middle. So if I ask you, I bet you could figure out, if I said, okay guys, let's look at this. Again, I know my drawings are just kind of yucky. Okay. Okay. So you've got a hole in the middle. So let's think about this. You have to figure out, I mean, if I said, what's the volume of that donut? Well, hopefully you'd think, well, I'm going to take the volume of the big part, okay, as if it were solid, and then I would take out the volume of the hole. And that's exactly what you're going to do. And so this was big R like it was before. So if I do pi times the integral, and I know we're going to have bounds on this, but just get my point. If I have pi r squared dx, that gives us the volume of as if it were solid. But I have to take out the volume of the hole. Now the volume of the hole is going to be from here, I'm going to call that little r, the radius of that hole. So I would take out this. And so most likely you don't want to have to integrate twice. And so it would be true that I could write this, so the washer formula is going to be pi times the integral, of course you're going to have your bounds from a to b, of big R squared minus little r squared. Okay, again it's going to be dx or dy. I'll put dx for now. But this is going to be your formula. People, make sure that you understand that this does not equal this. Those two things are not the same. So you have to think of it as doing big R squared minus little r squared. So let's go and look at our problem here. And let's see if we can get our drawing. So notice again that the axis of rotation, because I mean you know today's washers, but does not share a side. With the bounded region. So you have that hole, okay? It has to share a side. It might share a point, but it does not share a side. Now, big R is the same thing as we did yesterday. Big R is always from the axis of rotation to the outer part of the solid. Little r, so if I were drawing this picture, I would go, okay, big R is from the axis of rotation to the outer part of the solid. And this is still the same thing. Big R and little r are always perpendicular to the axis of rotation. So big R is going to be like that. Little r is from the axis of rotation to the inner part of the solid. So little r is going to be right here. It's going to be the hole. What's the space? And once I have that, I'm going to go to my formula. I'm going to say the volume by washers is the integral. Now let me get my bounds. You either get that by solving. You do have a calculator. I am doing dx because remember, if your axis of rotation is horizontal, just like this, you're going to be doing dx. And so those bounds, again, I can either do it algebraically. 4 minus x squared over 2 is equal to a y value of 2. I could solve that. Or remember, if I wanted to have the calculator, I have my drawing, I have my y equals, I could put y equals 2. And I certainly could find the x values of those intersection points by doing intersect. second calc intersect. And these end up being pretty nice. So I'm going to get 2 and -2. So whichever way you have to do that, you can. So my bounds are -2 to 2. Okay. Now, let's look at this next part. This next part is big R squared minus little r squared. I'm going to put a big bracket to make sure I'm integrating this. Now, what is big R? Well, just like we've done before, I'm doing top minus bottom. Big R is 4 minus x squared over 2 minus 0. So I won't put the minus 0. So that's big R squared minus, well, what is little r squared? Remember, that was 2. So what is the space between here? Well, if I do top minus bottom, that's 2 minus 0. Yes, you certainly could put 4, but I'm just putting it so you see the formula of big R squared and little r squared. And then I get on my calculator. You do need to practice typing this in. Remember as well that when you type things in, like I have this already stored in Y1 to kind of save you some parentheses. If I'm going to do this, I hit Math 9. And you know what? Usually these don't give you very many pretty values. So I'm going to go ahead and just stick my pi in there so I don't forget to multiply by it. I'm going to go -2 to 2. Remember, the calculator has a set of parentheses. So that's why I kind of write them so that your paper and your calculator looks the same. Do you remember that I have this function right here stored into Y1? So I'm just going to go Y1 squared, so that's big R squared, minus, I'm pretty confident I can do 2 squared in my head and get it right, dx, and I come up with that value right there. So the volume is going to be 93.829. Please do not forget to type it in right. If you typed it in like this, y'all, parentheses are a big deal, so you don't need to disregard the part of practicing typing it in, because you'd hate to have always invariably on a calculator portion, I'll have somebody that has this part correct and then this part wrong, which means they typed it in wrong. And those are points that you shouldn't lose. So let's look at the next ones. All right. Find the volume of the region bounded by the curves y equals x and y equals x squared, rotated where? Well, again, I like to kind of overemphasize my drawings. So let's do this. Okay, y equals x. I'll draw it first and then I'll make it better. And then y equals x squared. So y equals x squared looks like this. So do you see that my bounded region is this little flower petal, I guess, right there? Do you see that? So I'm gonna, again, I'm not a visual person, so I kind of like to only have my bounded region. So there it is. Now I certainly need to figure out, this one's drawing or revolving around the x-axis, so I like to dot that in. Do you see that this would be a washer problem? Because does it share a point with the bounded region? Yes. Does it share a side with the bounded region? No. So this is going to be a washer problem. So in my brain, I think, okay, I need to draw big R and little r. They're both perpendicular to the axis of rotation. Big R is from the axis of rotation to the outer part of the solid. Little r is from the axis of rotation to the inner part of the solid. And big R, rocket science, is bigger than little r. Okay, so make sure you draw it that way. So here's what I have. I have the volume. I'm going to have pi. I know I'm going to have all this. My axis of rotation is horizontal, so I have to do dx. And I'm going to think big R squared minus little r squared. I just have to fill in all that stuff. Again, I don't care the order that you go. I do have to find bounds. If I know it says calculator, but again, if it says setup, you could do this setup without a calculator. So if I set x equal to x squared, of course I get x squared minus x equals 0. I factor out an x, and I would get my bounds to be 0 and 1. So I certainly could do that. So my bounds here. Now let's look at big R and little r. You love it when it's the axis because your axis, your bottom is going to be 0. So if I said what is big R, well, which curve is that? That's x. So it's going to be x minus 0. So I'll just write x squared minus what is little r? Well, that one is x squared. And so there you have it. Remember, y'all, if it says setup but do not solve, then you can leave it just like that. Yeah, if you had to get this one by hand, your next step would be to clean it up, and you'd say, well, that's really just x squared minus x to the 4th dx. And you certainly, this is not one that I'm like, ooh, y'all can't solve this by hand. You could, but what I'm saying is, if many times on AP it says set up an integral, and on my test, set up an integral but do not solve. If they say that, why bother cleaning it up? Because if you make a careless mistake, you're going to miss it. They will give you full credit for what I have right there, so go from there. Now again, I want you to, every time I want you to stop the video. I don't think I have to type this in for you to see it. But I also want you to make sure that you are typing it in, stopping the video, practice typing it in the calculator, and making sure that you get this value for the volume, just to make sure that you are typing it in right. Okay. All right. So I have the same bounded region, but I'm revolving it around the y-axis. So y'all, it's all in the drawing. Here's my bounded region, and now I'm revolving it around the y-axis. Okay, several things. What does that tell me? Well, it's still a washer problem. So I know that I'm still going to have the same kind of format, big R squared minus little r squared. But my axis of rotation is vertical. And if my axis of rotation is vertical, I have to do dy. Now, which means a couple things. A couple things in that, for one, my bounds have to be y values. Now, I know it doesn't look like it on this one, but if you had found these bounds, you would have to say the bounds this way. And they happen to be the same because of my equations here, but I want you to be very clear. When I put this 0 and 1, it is because this has a y value of 0 and this has a y value of 1. I'm looking at these values and not the x's. So I would have to get those in terms of y. Now the other thing I have to remember what my two equations were. I'm going to write them here. Remember, they were y equals x and y equals x squared. Remember, when you're doing dy, your equations have to be solved for x. Well, this one already is. I mean, I could write it. You know that that's the same thing. X is equal to y. This one would be what? X is equal to, if I solve for x, you'd say, well, it'd be the plus or minus square root of y. Well, how do I know it's the positive one? Because it's the right side of x squared, which coincides with the positive square root. So you have to have your equations solved for x. So when you do big R and little r, well, let's get them in there. Big R is perpendicular to the axis of rotation to the outer part of the solid, and little r is right there. And what am I going to do? I'm going to do right minus left. Again, when the axis is the or when the axis of rotation is the axis, you know that you have 0 right here because that's x equals 0. So my right curve is y equals x squared, which coincides with the square root of y. Again, minus 0. My left curve is y, and there you go. There's my setup. You type that in, make sure you have it, and you should get 0.524. Okay, again, I'll type this one in just to make sure you know something. If I don't have that typed in already, you guys, you have to watch your parentheses. I always forget to do the pi when I'm talking. You do have to really watch your parentheses there. If you are not cleaning up, that's fine. Remember, with y's, I still just type in x's. So that's being squared there. So there's big R minus little r dx. And there's the answer. So some people like to clean it up just for their typing's sake, but again, it kind of just depends on you, and that's what you're going to practice with your homework and making sure you kind of get your system down. All right, last one. Same axis of, same bounded region. And remember, this was at 1, 1. Should have made that a little smaller, but that's okay. I'll extend this up a little bit. And my axis of rotation is at 2. So I'm revolving it around this. So that's kind of weird. But y'all, it's all system. It's all system. You know it's washers. It's not even touching it, so it has to be washers. So you know your equation is going to be pi. You're going to do your bounds. You're going to do all of this, dx, because my axis of rotation is horizontal. I need big R squared minus little r squared. Now I just got to fill in my stuff. Well, we already know the bounds were 0 to 1 because those are the x's, so I have that. Well, let's draw. Big R is from the axis of rotation to the outer part of the solid. Little r is from the axis of rotation to the inner part of the solid. How do we find the length of that line? Top minus bottom. And remember, if you're doing dx, you're solving, our two curves were x squared and x. So these, you want it in terms of x, so that's what you're looking at. So when you do top minus bottom, for big R, what's the equation of this top curve? 2. Minus, what is the equation of the bottom curve? X squared. Little r, what is top? 2. Minus, bottom was x, and there's my setup. Now again, I'll get on and type this one in. You've got pi times the integral. Usually these don't come out very pretty, so of 0 to 1. Okay, you've got that set of parentheses that does it all. I have 2 minus x squared, parentheses squared. So that's big R squared minus 2 minus x squared x. And lo and behold, I get my volume. 1.676. And there you go. So what I want you to see, again, is that you do the setup, and I'll be honest, some people, if I go back here, if I go back to my very first page, there are some people that actually just memorize the washer formula because they go, wait a minute, if it ends up being a disk, and some teachers just teach the washer, because if they share a side, what would little r be? It would be 0. And so big R squared minus 0, and you notice that you have the disk formula. So because this piece would just be 0 and would go away, and there would be your disk formula. So I don't want you to think of disk and washers as you know, two separate things. Most people with disk like that because it's simpler, but I want you to see that they're totally related and they have a lot of similarities. If your axis of rotation is horizontal, you have to do dx on both of them. If your axis of rotation is vertical, you have to do dy. So, and how you draw and things are the same. So, hopefully you can practice that and think it's not too bad. All right, peace out.